We're going to have Tim Strazzere presenting Go Forth and Reverse. First, though, a couple of quick announcements. We are streaming this live via the interwebs, so please take out your infernal devices. Make sure they're in silent mode as a courtesy to our speaker and our at-home audience. I also have a microphone. So if you have questions, raise your hand. I'll give you the microphone, again, for the folks watching from home. Quick announcents about our sponsors. BSides Las Vegas wouldn't happen without the generous support of our sponsors. Versebright, Protivity, Tenable, Amazon, and Source of Knowledge. Also, this is a volunteer-run organization and conference, so big thanks to the staff and volunteers who are donating their time to make this wonderful conference happen and supporting our community. Also, if you have any feedback for Tim, that can be given via the sched.org website, sched.org. And with that, here's Tim.
Thank you. Cool. Yeah, so welcome. Thank you, BSides, for having me here, and thank you guys for coming. We're going to do a talk on Golang, that goofy little gopher, and just a little quick who's Red Naga, since I'm with Red Naga. We just kind of band together. It's a couple people. We mainly do rooting of Android devices, IoT devices, that kind of thing. It's open to anyone. We accept blog posts from anyone. It's kind of like that old hacking and like CSGO kind of thing where all you need to do is take a picture of yourself eating the hottest pepper you can stand, and you're welcome to join the club. Everyone else has done different varying levels. Some people jalapenos, some people red nagas, which are the ghost peppers. If you check out our website, we have lots of different training materials that we've put together. The whole thought process behind this, and I think BSides as well, is we want everyone in the community to get a lot better because we don't want anyone doing boring work. So hopefully everyone gets an awesome set of tools, an awesome skill set, and then starts releasing things open source so that essentially no one has to do that really bad and boring work anymore. That also means that we can concentrate all our time on really fun tasks like hitting new devices, and maybe developers won't be doing these really silly things anymore. Specifically, who am I? Currently, I'm a security engineer at Cloudflare. Previously, I worked at Lookout and SentinelOne, which are both endpoint detection clients, one for mobile, one for basically desktops and servers. So a lot of the things I've learned over the years are trying to figure out how to unpack things really fast in an automated way, deobfuscate them, and try and basically reverse things as fast as possible so that we can confirm whether it's benign or it's malicious. And if it's malicious, what's it doing, and what do we need to protect our endpoints or customers from? And that's sort of where this talk came from. We started seeing a big outburst in Go malware, and we would just see these binaries getting dropped, and they were really weird, and we'll get into that a little bit later. But essentially, Go is a lot different than, let's just say, C. And then if you were trying to detect malicious binaries, or if you were actually going to be doing penetration testing on some kind of binary that someone has on a server, or something that's getting dropped on a desktop, you might want to find out where the quirks are and where things actually are. My GitHub's up there, my Twitter's up there, and if you like hot sauces, I'll send you some that I made myself. You might have to sign a waiver, and if you have really hot sauces, let's drink them. So again, why am I here? Go isn't necessarily new. It came out in, I believe, 2012, but it got a little bit of pickup. People are, Go aficionados already. You see it sometimes on job descriptions where, you have to have 20 years of experience in Go, even though it didn't exist that long. But, for reversing, I haven't personally seen many people talking about reversing Go binaries and what are the nuances of it and how do we get into the good bits of it. There's been lots of different malware. It's an interesting platform. And if you're a Go developer, don't throw anything at me. It's sort of like Java, or at least the concept of Java, of I can write code once and it will run anywhere. It's different from Java for many reasons, because it's actually fast, it's actually pretty memory safe, and it actually is nice to write the code. So this is sort of a thing that I grabbed from the one website, but basically things are going to be more efficient. you can write really fast servers in probably like 3 lines of code, and there's a huge open source community around it. So it's a really great tool, and you should check it out and see if like you want to actually use this just in your day-to-day development. I've basically been switching over all my personal reversing tools to start being written in Go. So I guess I'm a hipster. I do live in the Bay Area. It's kind of like that. But let's dig it in from the reversing side and what it actually looks like differently than, let's just say, C, because C is still that master language. This is just that simple hello world that you've probably seen a billion times. And this is what it gets disassembled to. It's really like a small, tiny binary, and you're basically going to have one function to look at. This is a screenshot of Binary Ninja. But so basically, if you took something out and you just reverse it, it's pretty straightforward. You're only going to have a couple functions, maybe a couple imports, but there's really nothing there. So if you had a really simple piece of malware, you're going to know exactly where you want to look into the binary. So it's low level, minimal, and it's fast. Why is Go different though? So that same example, we're going to end up seeing this, it gets a little crazy. Essentially, that one little bit can be, it can be compiled on any machine to either a PE, so that's going to be a Windows executable, an ELF, so a Linux executable, or a Mach-O file, which is going to be the Darwin Mac OS stuff. And then inside that executable, it's going to inject its entire framework and runtime in there. And then your code is going to be inside there. So if we were to look at this from a reversing standpoint, what we're going to see is okay, there's a start function. All right, let's go to start, because that's what the actual operating system's calling first. And we see that it's like, okay, well, there's some start, there's a call to main, there's a runtime jump, and that leads us over to, there's that runtime RT0 go. And this ends up being a relatively large function. And then we see this really awesome thing down there that is just a pointer that the disassembler didn't understand what that's a pointer to or why that is. That's actually being passed in there as a, here's the address of my process, and I want to start up a new process. That goes to runtime main. And so in runtime main, you're going to dig in here, and we're going to see that it actually has a call to main. So that was really easy, right? Like just that one line ends up exploding into these things that if you'd never seen it, you're just looking around, where's my main function, where's my main function? This is how you would try and get it from the entry point, which is start. So start main, runtime new proc, main. That's super easy, right? It's not super easy, and it's a pain when people start hardening it. And then again, this is Binary Ninja. This is what it looks like when you start digging into it a little bit deeper. We have over 2,000 or so methods in just a hello world binary. And this is all the runtime. This is all the things that Go is injecting in there so that it can try and run efficiently. This is what the normal main function looks like. We can see that we have a hello world being loaded in there, and there's all these other magic things, and there's this weird little runtime stack, more context, or runtime stack, no context, and then a jump back up to the front. So none of this code was anything I wrote. All I did was basically say print line hello world. We got this whole thing in here now. And then if we scroll down to the bottom of that function, that's that one function that I wrote and what I wanted. So there's a lot of things that are getting compiled in here. So you could see how it might get kind of confusing if someone was potentially trying to hide things, or if someone was actually writing something that's more than one line of code. So here's an example of when someone tries to make it hard to reverse, all they're doing is adding a strip flag. So maybe you've seen this when someone writes C code, they strip it out. This usually drops the symbols table. So then the compiler's like, I don't really know the name of anything. I don't really know what's going on, but I know there's a function. I don't know what it was called. And essentially what we see is now all those 2,000 methods on the left-hand side don't have names. So if you didn't already know how to get there directly from the start stub, which is going through all those runtime execs, all that stuff, we don't really know where any of these functions are, what their names might be, which is pretty common when you're trying to reverse a malicious payload or something like that. We also see that at least Binary Ninja looks at this and it goes, oh, okay, well, it's some bytes. I don't really know what's up with that. So you'd actually have to go all the way, find the main function, and then tell it it's a function because it couldn't figure that out on its own. So when we force change it, we now have that same exact method. So we basically said, this is a function. I want you to display it as a function and start disassembling it. And this is the same exact one. We still don't see any cross-references to any of the previous functions. And so that's kind of worrisome. So if we want to try and backtrack to the entry point or see if this code is ever used, it might be a little difficult. What we also see is the functions on the left where before it had all those names, runtime, no context, it doesn't know what those are called. So why should you care? This is a friend over at ESET. He basically spends his entire life looking at Linux binaries, and you should follow him on Twitter, and you can see lots of interesting things that he starts talking about. And it's a pain in the ass. He's been rebuilding these by hand a lot. We did some work to automate some of that. That's basically what this talk is about. But basically, he hates it, and it's really annoying because people are just basically saying, oh, Go has this awesome open source community where people have done crypto miners that are efficient. People have done SSH scanners that are efficient. So all you need to do is say, get that package, and then we all run out of the building because there's a fire. I'll try and keep going. Sounds like we got to evacuate. So yeah, essentially, like I was saying, I think I said it, I'm not sure. Go ahead. Okay. Anyway, it's really easy with only like maybe, let's say 200 lines of code to throw something together which is going to be malicious, it's going to start auto-scanning things, and again, it's platform independent, and you're efficient, so not only can you infect someone's computer, but you can be nice about it and have a low memory profile, and everything's just going to work. So, like I said, Go straightforward, it's easy to use, so that means it's easy for good guys, and it's easy for bad guys to use. Over the past year and a half or so, we've seen lots of different things pop up in the Linux arena, where it was like Linux Lady, Rex, Agent DT, because we don't like naming things interesting things anymore, or we just see them too much. There's also lots of proof of concepts out there on GitHub. So it's essentially lots of things saying like, hey, I thought it would be a great idea to basically write a DOS, and then I'm open sourcing it because I'll get a better job offer. I don't recognize that as like a good idea, but there are plenty of people who are doing it, and you do see this bundled into actual attack code. There's also Go Mimkats. So a lot of pen testers tend to be using Golang is what I've seen. I don't personally work with pen testers, but there was this interesting comment on Reddit that I saw someone say, and it's basically he can write a quick little binary that drops down, and since it's wrapped in all this runtime type stuff, it gives antivirus vendors a hard time to actually figure out what's going on. And then what this person was doing is they're basically like, I'm just going to make a call out to my server, which is generic. I just spun it up in maybe DigitalOcean. It's a new droplet. There's no IP reputation around this. And then they were just saying, OK, give me the code. And then it executed a payload. And they basically said, no AV user ever picks this up. I believe it because it's hard to pick up. In the AV world, what normally happens is, unless you're just doing straight whitelist or straight blacklist, and doing hashes of every single thing, which a whitelist can be protective. It's interesting. It means you have to verify every single thing. And if it doesn't match a hash on my whitelist, I'm not going to let it run. Blacklist is a little different, and it has its good sides. But the bad thing is, if I reconstruct something right now, it's going to have a new hash. So if they haven't seen it, they can't flag it right away. The other way people do detections is with heuristics, basically saying, I'm looking for this sequence of bytes. And this makes it hard for them. So again, run go time has maybe 2,500 functions of code. These change every once in a while through Go revisions. And then the malicious code, again, this might be like 3 lines of code. And it's surrounded by Go instrumentation. And so if you're going to look for it, you're going to be like, OK, well, maybe I'll choose a string, because a string would never change in a piece of malware, right? And so if they're importing libraries, you can't just say, oh, that thing someone pulled off GitHub that is also used by good people, and it's used by a bad person in this one instance, I'm going to label that as bad. And this is exactly what we see. If you search for Go malware, here's a post from 2012 where someone's like, what the hell? Symantec is flagging this. And I love the status unfortunate is what it was changed to. And said, oh, that sucks. Like, well. And then we have one last year where Kaspersky started flagging things. And this happens a lot because if the analysts who are making these changes in the engine are basically like, well, I've never seen anything like this. This is super advanced. They're usually just looking at the Go runtime. And then when they dig into the code, they're like, oh man, it has like, it can do SSH brute forcing, it can do this, it can do that. Again, that was code pulled off from GitHub. So we got it wrong again. So what we end up seeing is when someone strips the binary, and if someone hasn't already figured out like, how does the Go runtime look? What am I doing here? You could use things like bindiff. They provide some interesting stuff. But once they strip it, you're basically hunting for that little tiny segment in that huge bloated binary. So a lot of server-side apps are also moving to Go. It's memory safe, like I said, supposedly. There have been memory issues. That's an interesting thing that you might want to know for both looking at the source code and analyzing it with a disassembler. I found like a lot of expensive bugs when I've been doing some contract work where people are like, you can look at our source if you want. Some of them don't want you to look at the source, but they end up shipping you this Go binary. And a lot of licensing licensing code uses this. And so when you're digging into it, you end up seeing like there's logic flaws that you wouldn't actually see when you're looking at the source code level. But it's basically because the runtime might function in a certain manner, but when it's compiled, it's actually trying to do a little bit different of things. So I think it's important for developers to understand what's going on under the hood, and especially reversers. And then this is back to Michael over at ESET. Basically, I was tweeting, I was like, hey, has anyone seen any more malware? And he was talking to me privately and basically said, go look in VirusTotal, go search for a Golang string, and everything's going to be malicious. And it's pretty true. If you go through VirusTotal, there's probably like 10 gigs of Golang malware. You know, they're all similar strains. They all use their own little things. A lot of spreaders are being used, and there's some IoT malware out there. But basically, it's really easy to write. It's really easy to cross-compile, and it just works. So why wouldn't a malware author use it? So this is a screenshot of IDA Pro. And IDA Pro and Binary Ninja don't have the greatest support for Go. I understand why. They're not like bad tools because they don't have the support, but nobody's really been expressing interest in these things. So I was looking at some malware and doing some auditing of some binaries, and essentially I ran into a lot of issues. Up at the top, this is a colored version basically of saying like, what does the binary look like? Orange basically means it's a defined function. Red means it's an undefined function. So it might be code, it might not be code. I couldn't figure it out. And as we look on the left-hand side, left bottom side, we see that it only has about 1,300 or so functions. And we automatically know that that has to be wrong because the Go runtime has at least 2,000, 2,500. So if nobody's imported anything in here, well, you might not have all the functions, but you have some of them, but probably ones you don't want to look at. We also see that this is essentially what loading strings in Go looks like. And IDA Pro is like, I don't know, there's some values and some stuff. But if you wanted to really quickly assess this and be like, what's this doing? I see flag int, I see flag bool, I see flag string. Why there are no strings? And it sucks. So basically, we've identified a few things that we really want to actually start reversing. We want to be able to say, what are the functions? I want to be able to define all the functions really fast because I want to look for bad ones. Functions don't retain their name when they're stripped. So is there any way that we can rebuild at least like the runtime? And again, I tried this multiple ways because there's lots of weird strings in those binaries. I was like, all right, what if I build something in that Go version and then use Diaphoria or bindiff, and then I'll just do a match and be like, okay, that match, like this is the runtime match, that's the runtime match, and then you can kind of cobble it together like that. It works, but it was super slow. String loads can be funky. And the holy grail in AV industry, sadly, is if the binary has strings that look malicious, I'm usually going to say it's malicious. And that's kind of like the sniff test. If it looks like it's a licensing server, people are going to be like, cool, whatever. So if you want to make good malware, make it look good, and don't put words in it like swears or cussing out AV people, because people are always like, oh, yep, that's malicious. Let's detect it. I don't even know what it does. And then again, so the Go version might be interesting for if we can actually identify which version of the runtime this was compiled with. Maybe we'll do that with different heuristics or something like that. But if we can tell what version of Go it was, we can tell what runtime we might be looking at. So we're going to dig into this. And essentially, we want to automate all this work because we don't want to be sifting through it every single time a file comes in. Especially in the AV industry or the pen testing, usually you're getting paid potentially hourly or by, you must verify this many binaries at an AV place, Or if you're pen testing, if you don't get anything done in the first 10 hours, you kind of look bad to a client sometimes. So tackling functions. This is, again, that hello world example. And what we're seeing right here is we got the function start. And I don't actually have all the locations next to it because I wanted to show it in the pretty graph view. But essentially what we're seeing is the main is the top. The main is the top with that first move. And then actually at the bottom, all the way to the bottom at the function, we have that runtime more stack, no context, and a jump to main. So this is consistent to pretty much every single function that will ever be created in Go. And this is how they do the catching of the panics. So if there's any errors in here or something happens that we're not sure about, it's basically going to catch into there and be like, what was the context of this? And if it was still okay or something bad didn't happen, loop back up to the top of the function. So this is kind of like a template for every single function that we want to reverse. This is that same function, and this is actually really interesting because Go, the design of Go is meant so that we can reproduce binaries byte for byte, so that if you compile something on your machine and I give you a hash of that, or you give me a hash of that, I can then compile it over here, and if I was using the same framework, the binary should be identical. So this provides us a really interesting way to basically say like, okay, if I mangle this binary in one way, and I strip it, and then I go over here, and I have the one that has all my symbols still in it, I can compare the two and be like, okay, so where'd that information go? Did it go here or here? So this is the exact same binary, it's just been stripped. So we still see that there's the top of the function, and the bottom of the function has that call. We don't know the name of that function anymore. But it's exactly the same context wrapping style. And if we actually look at that function that was, I believe it was the runtime no context. If we look at that, we see that that cross-references every single function that we've seen. So again, this is how every function is going to look like. So we know that if we could find that function, we might actually be able to work backwards and basically say, okay, I know what this function will always look like because it's always compiled that way. And then I can cross-reference back and start recursing and saying, okay, now I know all the other functions and I know all their sizes because that's the last function call and it has a loop up to the top. So now all I need to do is identify one function. And if we dig into that, we see that that one function branches into runtime more stack. And this is the entire function. It is always like this. You basically kind of need to profile. So like there's Go 1.6, 7, 8, 8.3. Sometimes this changes, but essentially there's this one little call at the end, the move D word. That's the only time you will ever see this in a Go binary, is in this one function. So it makes it really easy for us to identify this. So essentially we find that as our hook, and now we know like a pseudo solution where basically we're going to find this, we're going to go to the function that called it, and then we're going to cross-reference every single function that calls that, and we know that that's the second to last line in the function. So we now know the end of the function and the beginning of the function, so you can tell Binary Ninja, or you can tell IDA Pro, or whatever kind of disassembler you're using, say like, that's a function, that's a function, that's a function, anything that references that type of code. So what we end up seeing is, again, this goes back to, up at the top, orange means it's defined, red means it's not defined. So if we write some code, we already have a Python module that I wrote that did this, all we see is it's pretty nice. So now there's only a couple things that are undefined that we probably don't care about, maybe we do, but at least there's only a few things in that stack that you need to look at to say, wait, that thing that's undefined, is that good or bad? And then we also see the script output at the bottom. We now have 2,000 and almost 500 functions that we just found from that were not known to be functions previously. So that's pretty cool. So that means that we don't have to dig in here and be like, okay, were those functions, were those data structures, what is this? We automatically now know where every function exists. So that was the first step. So the next one we're going to do is, can we rebuild the actual names of the functions? So if you start digging into the binary and you did like maybe just the strings on the final, this is actually what a lot of people had been reporting as like, hey, this binary is malicious because when I ran strings, I saw that it said main run DDoS. And so I was like, okay, it's probably going to do a DDoS even though I didn't figure out where that function is or how it does it. So a lot of people were just posting screenshots of, look at this new malware, here's a string table, and I saw this string. And that doesn't really pass my sniff test of, you're probably right, but that just doesn't sit right with me. So we see the strip binary on the left, and we see the normal binary on the right. So basically, we do see that the function names are very nice when we have a normal binary, but the stripped one's a pain. So we want to be able to start seeing if we can migrate from a stripped binary into a normal one, maybe rebuild the symbol table or something, not really sure. An interesting bit in the strings table, or excuse me, for the string load, IDA did pick up that there was a string load, but it also thinks that that string is huge. And so if you went into that part in memory, you'd go, okay, what is this? There's a huge blob of strings with no null bytes in there. So it's not a normal C-type string where it's a null-terminated string. So when we start digging, we find that there was this weird segment in the actual binary, and it says go PCLN tab. And so if you dig into the source, it's pretty interesting. This is something that doesn't get stripped out when you say you want to strip the binary, and it's actually used by the Go runtime. So it uses this so that it can use some reflection. And essentially what happens is they keep this so that the Go framework understands what's going on. So if you hit a panic and you had that stack trace sort of like Java, you basically go, oh, okay, I know what function that was from and around what line it was. And so this is some extra data that's in every single stripped binary. And essentially there's a header, there's a function count, and then each function is essentially, it's an address to the function, and then it's an offset to the function name in a string table. So this is awesome for us, because this means we can basically rebuild those binaries really fast and hopefully in an automated fashion. And so what we're hoping we can do is we take all these unknown functions and we're going to be able to rename it to what the binary actually knows they are. And this is what happens when we run our little script. It is really easy. Essentially all you do is you look into the source of Go and you're like, oh, that's the structure. Now let me just write a little code that goes in there and says how many functions am I supposed to look at, parse each structure in there, and then you can basically say, oh, that's the start of the function, let me rename it. And this is good for pretty much any binary. I've never seen anyone strip out that section, because again, Go does rely on it for some functionality. So people are still chatting on like, can we mutate it some way? Can we remove it? Will that mean that the binary might crash more? No one's really solved it, and clearly the Go developers are not trying to help people basically create really hard, destructive binaries. So basically, we're able to rebuild the binary so far. So this was a stripped binary, and we're able to now have easy to read function names. And we also found more functions than we previously already saw, and we have about 7,500 functions. And this was for a really simple DDoS spreader. So it was basically something that was looking for weak passwords, and it was getting into different devices, and then it was just DDoSing on commands. And someone had stripped this, and now we're able to rename it. So it's really easy to figure out what we're doing. And this is important again because there's so many functions in this binary. We see that there's over 11,000, and none of them had names before. And now we look at it, and we can see that there is a main init func1, func2, and then there's a main func1, and there's the slave server and the get external IP. That's the only code that the malicious author wrote. All other 11,500 functions are completely useless to us when we're looking at this. So if you weren't able to rebuild that, you're going to be like, oh gosh, what am I looking at? This is going to take so long, and then you're probably just going to quit your job and go do something maybe a little easier, or I would. Cool. So essentially, we've now figured out that we can rename every single function, and we've actually been able to map out where all the functions are. So for string loads, it got a little interesting, because honestly, I had no idea how any of this was working, and I actually did this before I'd ever written any Go code. So this tends to happen when someone's pulling in vendor code from a different package. You end up seeing the function names looking similar to this, where it's someone on GitHub had posted this, and the function name ends up being github.com/this/that, and then it's actually the file that it's referencing. So this helps a lot when you're reversing, because you don't actually have to reverse any of those functions unless you assume someone's trying to give you a false flag. So you can just go to the GitHub page, and you just look and see what the code's doing. And so if we looked at this one very specifically, this was just something to help someone do some logging. And so the login would be easier for them. And we see what the actual arguments are for this and what's being passed in. So I gave you this example because we know it's going to be taking a string because it's a logging statement. But this is the function, and I don't see a string because nothing's identified as string. But we do see that weird little pointer that's getting loaded into EAX. And if you were to look into the binary, we notice that, okay, it found that there's a reference here, and then there's this string. And if you look, there's no null bytes, but we do notice that there's a weird thing where two lines below the load, we see hex 10, and then we notice that it looks like maybe a string that's that long. We're not really sure. And then if we dig into it in a hex editor, we do see, okay, yeah, that looks a little easier. It's easier to read. It's not vertical. And this is just a blob of strings. And this is essentially how Go has a string table. So if you've ever done reversing in Android type things, it's interesting because I'm not sure if they like talk to each other or this is just a good programming language way to like group things. But essentially they have a string table and they're grouped the strings by the length. So all the strings that are one character are together. All the ones that are 2, 3, 4, all the way up. And it's just this huge blob. So what often happens is disassemblers see this and they're like, cool, that's a string, and all strings are terminated by null, except they're not. So you end up having this huge, 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 huge string, and it's like, yeah, it's loading this string, and you're like, no, it's not loading like a 9,000 character string. It's much shorter than that. But now we're able to basically say, okay, so we see something loading a pointer, and then we also saw that it gave its length. And that's because the strings are a structure of the data and the length of that data that it represents. And so if we look at that example, what we see is if we went to that offset and then we create a string of exactly 0x10 bytes, we get a good string that's actually there, and you could verify this by actually dynamically stepping through this. And then here's another malware that we saw, and basically you're stepping through and you see the strings loading because we're doing this dynamically, and we're like, oh, okay. It can use different registers, it kind of looks different sometimes, but all the string loads, it always has a pointer to the location, and then it also knows what the size of the string it wanted was. So we're able to automate this and basically look through heuristically, and we're basically going to go, okay, I want to find where there's a pointer being loaded into a couple different registers. For different platforms, you might, like if it's 64-bit versus 32-bit, you might have to whitelist certain registers and certain patterns, but you end up making these sets of heuristics to go through. And you look for both the pointer and what's getting put in there, and then also looking for like a length check. And what we're able to do is we can just automate all this work, which just makes our life a lot easier because now we're not trying to go through and look at, just do a strings command and be like, okay, maybe that's used here, I don't really know. You don't have to do this manually with, again, 11,000 functions potentially. So this ends up bringing us to the last point that we were looking for, was these heuristics change based on the version of the runtime. There's still binaries out there that get submitted to VirusTotal or getting dropped, and they're Go 1.2. So the heuristics that you might want for 1.2 to try and load all the strings end up being different than the ones from 1.83. They're getting a lot more efficient in their usages of loading. So sometimes now you might see actual strings being loaded in a branch where it's, it's a switch statement, and it's like, okay, load this offset, and then everything all comes down to this one little bundle. And then there's about like 40 other switches that are doing the same exact thing. So you can't look for these simple heuristics. So we want to be able to fingerprint the actual binary and see what version it is and what heuristics I should apply to that. And this also helps when you're trying to do, let's just say, a Windows PE file versus a Mac OS Mac O file. And so, like I said, heuristics can break, so we want to look for different ways that they're actually doing. So we want to have good heuristics that they can be a little brittle inside the version, but we want to actually be basically typing what version of the runtime we're going to be looking at. And there was this one function that we noticed was doing this, and it's runtime sketch init. And honestly, I don't know what any of this code does, but I do know that when you looked in the source, it was saying, what's my build version? And if we look towards the bottom of this, we do see that there's runtime underscore build version dot string and dot length. Essentially, if you actually look at the code for the Go runtime, there's a bunch of comments that say, we should never not know our own runtime, so this code will never be used, but this is a check to see, was it actually set? And if it wasn't set, they'll drop in unknown. But what we end up doing is we follow that structure of a string again, and we end up seeing this is the structure of a string, and it's saying I've already loaded this in at a runtime for a runtime build version string. There's an offset, and there's a number, which is actually the length of that string. So if we were to go to where that offset is pointing to, again, this is one of those strings that's dropped in a huge vat of strings, basically, with no null bytes in between. And now what we're able to see is that, okay, that says Go 1.8.1. So now we can programmatically figure out which version it is, and then we can run different heuristics based on that. So this ends up being interesting for us in multiple ways. So now we've fixed all our tools so that we can basically drop in a Go binary, where you run these, and we basically know every single function name. We already know every function that we might want to step into, and we have all the string loads, and we know the version of Go that was used. And going back to the AV industry, often you want to try and profile your attackers. So even if maybe they changed all the strings, you might see a certain region always pushes binaries with a specific runtime. This is a way you can start profiling actors. So this is a little flimsy, but this is kind of along those lines of what you might be thinking if you want to say like, oh, like who's an APT, who's not, if you want to use that dumb word. So issues are all handled. The code's up there. I need to push some actual new heuristics to it that I developed for this talk. But this is up there, and this is essentially this is a loader for IDA. So once you open up a binary in IDA, this is going to go through, and it basically implements all that pseudocode that we were just talking about. I also have one for Binja, Binary Ninja, and I'll be releasing that shortly. If you don't already have a license for IDA and you don't want to steal it from all the AV vendors who leak it out to people, which thank you for them. That's how I learned when I was a kid. Binja is really cheap, and it's a great tool. And if you're just trying to tool around and figure out what's going on, you should pay for that. It's like 50 bucks. If you message the guys, they're really nice. They're actually around DEF CON probably. They'll give you a free license if you're like, hey, I'm a student and I can't afford $50. If they don't want to give it to you, message me. I'll buy one for you. People should be able to use these tools, and I know it is very expensive, so that's why we're releasing the tool for Binja as well. So now that we've fixed all our tooling, this is my most favorite part, is often that we get to just break everything again. So, when we were working with malicious binaries a lot, people are like, why are you going to invent bad ways and to, break your own tool set? And honestly, I always tell people, this is kind of like doing recon and also trying to force funnel bad people or even good people in a certain direction. If there's no way to break a tool today, someone will pay someone to do it. But if we say, oh, you can break things this way and you do these things, you can develop your tooling to actually look for those signals. So you'll end up seeing like, oh, kiddies are using that toolkit we dropped. But there was a more advanced way to do it. We just didn't figure that out yet. So you'll see more advanced actors are like, oh, yeah, OK, that's how you break stuff. I'll go a step further. And if you have your tooling looking for that kind of stuff, you end up seeing, oh, that's a really advanced person who is doing a method that I was hinting towards, but I never released code for. So you end up seeing these things trip in your environments a lot earlier, and it ends up being for interesting stuff. And you never know. Maybe you'll call them Fancy Bear or Polish Bear or something, or Judo Chop Bear. So there's a friend of mine who wrote, it's called OG, OG, I don't know if you know how you would pronounce it. It's under the MIT license, and essentially it pre-processes your Go code prior to you compiling it. So if you know a lot about, let's just say, the Java environment, this is where ProGuard would come in too. So you have your source, ProGuard changes things, and then you compile it. And as a developer, what you end up having is you'll have like this mapping file where it basically says, that was my main function, but now it's transformed to this. And if it crashes on my customer's device, you can get a stack trace back, and that stack trace is meaningless to anyone else because it's like A.B did this, and then Chinese symbol plus that did that. And if you were an attacker and you got that stack trace, you'd be like, I don't know what's going on. I know the chain of events that occurred. I don't know what any of them are. But you as a developer end up having this little mapping that you're like, oh, OK, I know exactly what method that was because this Chinese symbol was main, this one did that, this one did that. So this guy wrote the preprocessor, which basically is just a set of AST parsers. And it goes through, and you can basically do anything for it. He developed it so that he could write like, oh, instead of wrapping the code like this, I just want to write the word try in brackets. And so then try in brackets would always be mutated out to the actual Go code that was necessary to do those trying. We wrote it so it's basically an obfuscator, much like ProGuard or DexGuard. So this is a sample. And essentially, this was a backdoor that I had found in a binary that someone was distributing as a poker server. I don't know why. Like they were basically saying, hey, you guys should run your poker server on a production server in the cloud because, I don't know, they don't like GUI and they want to play poker a lot, I guess. I don't know. It's really strange. but they did have some infections. We actually were able to take over the C2. But this is essentially what the code looked like when you reversed it. So we basically see it's just, it has a backdoor port, everything, and then it branches out to a handle connection to actually do any of the work. So now if we ran this through the obfuscator, or GoGuard, is what we are releasing, is it just gets changed down to this. You still understand what's going on, you still see what it is, but essentially from a reversing standpoint, what we see is, this is what it looked like before we obfuscated it and before we ran it through GoGuard. We see all the function names on the left. Yes, we could have stripped it, but as we just showed, we're able to rebuild all that stuff. So when you run it through the GoGuard, what essentially it does is you lose the ability to rebuild everything to a nice name, because you've changed all the nice names to annoying names. And there's countless ways that you could change the mapping where there's known bugs where Chinese characters are not fully accepted in lots of versions of IDA. So that breaks all the free ones that people, or the free versions of IDA that people have downloaded to try out with someone else's license. This is a great way that we can actually just break all the binaries, and we can break all the tools that people are currently using that we just had fixed. So there's an easy way to solve this, and there's an easy way to map back, and people have done that for Android countless ways. There's really interesting academic papers about this, but we're not going to touch that in this one. I leave it as an exercise to you guys to write the next post, come up here, do a talk, that kind of stuff. But so again, there's the Go reversing primer that we've already posted. It will help you doing some reversing, just both generically and Go specifically. The Go lang loader assist is open sourced already, and I do have to push some more heuristics for that for Go runtime 1.8 and above, because they did change some different things. But I would say please go to that and help commit to that. I leave a lot of the easy bugs to people because I think it's a great way to start getting into the open source community and start giving back. And then also you can build a little bit of reputation if you'd like to do that. And then the Binary Ninja version of that script is also going to be released when I get internet access this week. GoGuard is also going to be released. And that again should be able to help people in hardening their binaries. Nobody's really doing any hardening other than the stripping, which we just showed is pretty much useless. So good luck hunting. Thank you for coming to the talk. Thank you for staying for the talk, even through a fire alarm. That's commitment. Thank you. I'll buy you all a drink. These are some good people you guys should follow. They have really interesting stuff, and a lot of them work at AVs or bounty programs, and there's really interesting stuff. So if you guys have any questions, I can take those now, or we can chat later or something like that. But thank you for coming, and also please donate to some of the NPOs that are out there. EFF is very important to everyone in this room, and especially in this country, and interesting times that we're at. There's also a really cool booth out there, Hack for Kids. Go donate. The fact that you can come to this conference means we are all very privileged. Donate $5, donate $10, donate $20. It's a tax write-off. You can get all the write-offs that the president gets too. So just go donate and donate to an organization, and let's all just do some good things today. So thank you.